Section 5.4 talks about the comparison test. So suppose we have two series, n equal 1 to infinity, n equal 1 to infinity. And suppose that b sub n is larger than a sub n. Now those terms, both of them must have positive terms, which means a sub n is, actually if I make that bigger than or equal to 0, that will do the trick. So they're always positive. Suppose that b sub n is greater than a sub n. So we have two useful conclusions and two useless conclusions. The useful conclusions are if the bigger converge, then the smaller automatically converge. If the series of the larger b sub n converge, remember they go this way, then the smaller converges automatically. That's what the comparison test says. And if the smaller diverge, then the bigger diverge automatically. If the smaller diverge, what's above it diverge. Now the two useless cases, if the series of b sub n diverge, that doesn't tell you anything about the smaller. And if the series of the smaller converge, that doesn't tell you anything about what's larger. So the goal is to look at a sequence, and again a sub n, they're talking about the series n equal 1 to infinity of 2 over n into n plus 1. This is how we start those. We start, if you see a number, get rid of the number, so we could make that a p series. Take n plus 1 and n. Always go left to right. Start with what you know. This is definitely bigger than that. Now tag an n on. And when you put 1 over, the sign switches. Meaning, if you have 5 is less than 10, when you put 1 over 5 is greater than 1 over 10. The bigger the denominator is, the smaller the fraction is. And then you tag the 2, so multiply by 2. So here we're looking at 2 over n squared. Now you want to be really careful. You want to say this is a series. P equal 2 is a series. If you don't write the summation notation, that's a sequence. There is no P sequence. P is greater than 1. The B equal 2, which is bigger than 1. Therefore, this series converge. Therefore, the series n equal 1 to infinity of 2 over n into n plus 1 converge by the comparison test. Notice here I have two series. I have to relist the series every time. So that's basically it. That's how it works. Now you got to be cautious how you play this. Now I'm going to give you a trick for natural log, since that's going to come up a lot. And here we go. If I have f of x equaling natural log of x minus x. So this is a function. If I take a derivative of it, that's 1 over x minus 1, which is 1 minus x over x. If I check where does the derivative equal 0, where does the derivative not exist? Derivative does not equal 0 when x equal 1, and the derivative does not exist when the denominator equals 0. Now when I get to my testing, since we're dealing with natural log of n, we know that I shouldn't worry about anything less than 1 because all of these start at 1. I pick a point to the right of 1, say 2. If I put 2 in there, that's positive. And 1 minus 2 is negative. If the derivative is negative, the function is decreasing. If a function is constantly decreasing from 1 all the way to infinity, then we have an absolute maximum at x equal 1. And what would that be? That would be f of 1 is an absolute maximum. That's natural log of 1 minus x. Actually, which minus 1, which equal negative 1. So we are aware that this is an absolute maximum. the graph, oh, we don't have to look at the graph. So we know that natural log of x minus x is less than or equal to -1 for all x on its domain. And if I add this to the other side, natural log of x is less than or equal to -1 plus x. And if I look at this and x, wouldn't you say x is bigger than this for sure? So what does that mean? Therefore, natural log of n is less than n over the domain of n. Anytime you see a natural log, you are allowed to come in and say, look, I'm looking at natural log of n. It's going to be less than n. And from now on that I proved this for you, you could use this all the time. Multiply by n, and if I square both sides, if I put 1 over, that will switch, but we have a problem because this is 1 over n to the 4th. This is a p-series that converge, but that's smaller, so that's didn't get me anywhere. So we approach this another way. N natural log of n, we say that is less than, no, bigger than n times 1. Natural log of n is bigger than 1, but you have to, if you look at the graph of natural log, it's 0 at 1. You have to reach e squared for it to become 1. So e squared, actually e is 2.71. So that's true if n is 3 or bigger than 3. Let's go that way. Okay, well, 1 over no, and then you square it, right? So 1 over will flip that. So now I got 1 over n natural log of n squared is less than 1 over n squared. Make sure you make that a series. That's a p-series bigger than 1, therefore this converge. Therefore, the series n equal 2 to infinity 1 over n natural log of n quantity squared converge by the comparison test. Now again in section 5.6 we deal with all factorials, but it's a good practice to get out of the way. N, n minus 1, n minus 2, 3, 2, and 1. And we're going to be looking at a bunch of, let's see, let's take n and n minus 1 and see how that works. If I put a 1 here, a 1 here, dot, 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 a 1, 1, and 1. Let's see. So for sure this is bigger than that. And we know that because, let me see, if I put n by itself, it's an issue. We know that that's bigger than that because I made this 2 a 1, which means this product is greater than that. So 1 over will switch this. 1 over n factorial is less than 1 over n into n minus 1. Now we have a small problem. So this is the comparison test. When we learn the limit comparison test, there is a way of figuring this out. Now we want to check and see whether this converge or diverge. We have this series. We want this to converge for this to converge. If this series diverges, then it's useless. That's why I didn't take just 1 over n. If I ignore this and put a 1 there, then 1 over n will diverge, and that doesn't get me anywhere. Well, this one, we're going to say, look, that's positive, that's continuous, that's decreasing. And if I integrate 1 over x into x minus 1 dx, now you're aware that this is a over x plus b over x minus 1. Once we learn the limit comparison test, there's no point in using the integral test. So this is going to turn out to be the integral of -1 over x plus 1 over x minus 1 dx, which is the limit as t approaches infinity of natural log of x negative plus natural log of x minus 1 evaluated me just fix this part. Evaluated from 2 to t, because I can't choose one anymore, I limit that. So that is the limit as t approaches infinity of basically negative natural log of t plus natural log of t minus 1 minus negative natural log of 2 plus natural log of 1, that's a 0. Two logs with a minus I could combine into a single log, say natural log of t plus 1 over t, t minus 1, not please. And as t approaches infinity by L'Hopital, that's the limit as t approaches infinity of natural log of 1 over 1. So that's 0, and I'm left with natural log of 2, therefore it converge, and this was bigger if you see. Therefore the series n equal 1 to infinity of 1 over n factorial converge by the comparison test. Now again, in section 5.6 there is a ratio test, and once we learn that, that's what we're going to be using on all of these problems that have a factorial or an exponential. Looking at this, we say, okay, look, we have sine squared of n over n squared. This is easy. Why is that? Because sine squared, the biggest it could ever be is 1, and this series p equal 2 bigger than 1, therefore it converge. Therefore the series n equal 1 to infinity of the sine squared of n over n squared converge by the comparison test. Again, here they're saying use the comparison test. I am, but in general on a test you could use any test you want. That saves you a lot of pain. We're looking at 204. Now this is how we start. We start first by talking about, look, we want n to the 2.3. Start with the denominator. This is definitely bigger than that. And if I put 1 over, that switches. Now, if I tag n to the 1.2 minus 1 and n to the 1.2, I multiply by that, that stays the same because that's bigger than 1. And this is also less than. Now I could split it up, or I could say, look, it's bigger to get rid of the 1. Make sure if you're playing this game, the inequalities line up. If not, you got to figure out from here. You could split this up, separate it, but this is easier. And this is 1 over n. 2.3 minus 1 is 1.1, right? 2.3 minus 1.2, 1.2, good. Series p equal 1.1 bigger than 1, therefore this converge. If this converge and it's bigger than that, therefore the series n equal 1 to infinity, n to the 1.2 minus 1 over n to the 2.3 plus 1 converge by comparison test. Now again, in the second half of this section, we're going to learn about the limit comparison test. That's going to save you a lot of steps. It works just like the comparison, but there's a limit involved. Similarly, we're looking at this problem, and the way we start, we say, okay, let's get rid of one of those. Well, let's see how this works. If I start with n to the 4th plus n squared and n to the 4th, this is definitely bigger. If I put 1 over, that switches. Taking a cube root of both doesn't change the fact, and multiplying by 4th root of n doesn't change that fact either because that's positive. So here I'm looking at n to the 1/4 divided by n to the 4/3, and that is 1 over n. I'm going to take 4/3 minus 1/4 all over 12. That's 16 minus 3. That is 13 over 12. Hopefully I didn't make a mistake. Again, make sure you put a series on this, n equal 1 to infinity. P equal 13 over 12, which is 1 and 1/12 bigger than 1. Therefore, it converges and it's bigger. Very good. N equal 1 to infinity of 4 radical n. Anytime you have more than one series listed, you have to restate what you're trying to show. Do not assume I'm going to know what you're talking about. And here's the final list. I look at this problem and I say, look, I'm going to take n plus 1 and n. This is bigger. 1 over, we'll switch this. Well, multiplying this by 2 doesn't change that fact. If I write this as 1/2 the series of 1 over n, I have a problem. This diverge. It's harmonic, or p equal 1, but this is bigger. That doesn't get me anywhere. And if I get rid of n, if I say look at n plus 1 and 1, this is bigger. 1 over will switch, right? And multiplying by 2, say, okay, well, the series of 1/2, well, the limit as n approaches infinity of 1/2 doesn't equal 0. This diverge. We have a big problem. We're not sure how this works. And this is where our limit comparison test comes in very handy. Of course, I could use the integral test and proceed, right? I could use the integral test on this problem and no harm done. Integrate, that's 1/2 natural log, I know this diverge. Or this is what the comparison test states. Comparison test says, look, if you have a series, compare it with another series. What dominates the top? What dominates the bottom? First, you need to know, does this series converge or diverge? If you take the 1/2 up front, this is p equal 1 diverge or harmonic. Then what you do, you take the limit of the sequence. You take the limit as n approaches infinity. It doesn't matter which order you put this in. Limit as n approaches infinity, multiplying by the reciprocal, that is n over n plus 1, by L'Hopital, limit as n approaches infinity of 1 over 1, which equal 1. Now watch what this series says. This series says, you're given one of those. You're going to come up with this series. You're going to make this series. For this to work, you really have to figure out what dominates the top and what dominates the bottom. And this is what's going to happen. They're both positive. Comparison and limit comparison test insist on the terms being positive. If you take the limit of the ratio, it doesn't matter in which order. And you get a number that's bigger than 1, bigger than 0. As long as it's a finite number. Therefore, either both converge or both diverge. Therefore, both, and since I showed this diverge by limit comparison test. So this is proof by example, or shown you by example. So I could use the comparison test. If I see a number, I could have did that on multiple of those. I could have did that on this problem. I could have did that on this problem. I could have said the top dominates by 2, the bottom dominated by 2, and squared. And as you notice, that's what you end up with. But the limit comparison test works more efficiently if you just add the limit. So I have a series. I'm going to create another series by taking the dominating term of a sub n, and I'm going to show this converge or diverge. Once I show that, this limit should be bigger than 0 because I'm taking the dominating and just playing with that. What that allows you to do, that allows you to eliminate the numbers that are standing in the way. Let me just see if we should do 1, 2. Oh, okay, down video will do. Here's another problem. This is going to take you back to the section of L'Hopital. You need to remember, if you have a trig, you want to take the trig and match it with its angle. Same thing with log. You want to match it with the argument. The argument, what dominates over this? The top is dominated by 1, the bottom by n squared. Series, this is p equal 2 bigger than 1, therefore this converge. Now what? Now I'm going to take the limit as n approaches infinity. So remember, if you have natural log of whatever, a, you want to compare that with a. And if you have the sine of beta, you want to compare that with beta. So if this is the actual series, this should be the one you're going to come up with, the series of a. If this is the actual series, you want the series of the angles, so that when you divide them, you get 0 over 0, infinity over infinity, and you proceed from there. This is natural log of 1 plus 1 over n squared divided by 1 over n squared. That approaches infinity, natural log of 1 of 0 over 0, and that's the case. Now, I'm going to use L'Hopital on this. That's the limit as n approaches infinity. Derivative of this is 1 over 1 plus 1 over n squared times the derivative of n to the negative 2 is negative 2n to the negative 3. Negative 2 over n cubed. The derivative of n to the negative 2 is negative 2 over n cubed. And you notice these cancel out every time. Same thing happened with those. That is the limit as n approaches infinity of 1 over 1 plus 1 over n squared. That's a 0. That's a 1 bigger than 0. Therefore, both, and again, whatever you concluded there, converge by limit comparison test. And the reason here I don't restate this, because I'm saying both of those, the one that I created and the one that was given, both converge. So you could use, if the comparison test doesn't work, the limit comparison test will most likely work. Now I'm looking at the last example that I have, and I'm looking at this. What dominates this? Well, let's see. This is dominated by n squared. And the reason I know that, because this is going to be insignificant compared to that. So series p equal 2 bigger than 1, therefore converge. So again, the dominating term of the denominator. The dominating term, if I have a polynomial, I take the highest power. The sign is not going to do anything except isolate this back and forth. Now, all what I have to do is take the limit as n approaches infinity of 1 over n squared minus n sine of n divided by 1 over n squared. That ends up multiplying. And again, you can put those in any order you want. It doesn't matter. That ends up being n squared over n squared minus n sine of n. And if I divide by the highest power term of the denominator, I could use L'Hopital, of course. Divide by n squared each of those. That is 1 over 1 minus sine of n over n. As n approaches infinity, that will approach 0. I'm left with 1 over 1, which is 1 bigger than 0. Therefore, they both, and we agreed here, converge by limit comparison test. Not stating what test you used will make you lose more than half credit. And there it is. That concludes this section.